Okay. Now, here's another place. When a reaction is at equilibrium, when we're finished changing, right, Q is equal to K, then. K is just sort of what we have after we've reached equilibrium, right? Okay. Q is equal to K. When we're at equilibrium already, what is delta G? Because we're not changing anymore. Delta G defines what direction we're going to be changing, right? So if delta G is negative, we're going to be producing more products. If delta G is positive, we're going to be producing more reactants going forward.
So then delta G would be 0.
Delta G is 0 when a reaction is at equilibrium. Okay. So, take a look at how this works. Delta G is 0 when Q is equal to K. So that actually gives us a much more interesting equation here, right? The standard delta G right? Standard conditions related to the equilibrium constant, which we had 2 whole chapters on. Okay? So it all came from the fact that Q can make our standard delta G bigger or smaller. Okay? But once we reach equilibrium, we're not changing anymore. Okay? We don't have a delta G going forward. We're just sort of standing still. So then the standard delta G can be related directly to the equilibrium constant. Okay? So this right here is the second important equation in this chapter. The first one being the definition of delta G by delta H and minus T delta S. This one relating standard delta G with the equilibrium constant. And we've talked about this a little bit already, right? And that a negative delta G means we're producing more products. Okay? Let's figure out how that would work. If we're producing more products at equilibrium, okay, K would be what? If we're at equilibrium and we're product heavy at equilibrium, what would K be? K would be greater than 1. Okay, so we would just be having some kind of value, the natural logarithm of something greater than 1. Okay, negative of that means that this is less than 0. So let's just write a little table here. Okay, K greater than 1, delta G less than 0. Okay. With K, the tipping point between product and reactant is 1 because it's a ratio, right? More products over reactants, that's greater than 1. More reactants than products, that's less than 1. Delta G is greater than 0 then. Okay? So taking any kind of logarithm changes something from being centered around 1 to something that's centered around 0. Okay? Because that's fractions, right? Top heavy and bottom heavy fractions. 1 is their tipping point. Okay? But actual energies that we've talked about all along, energy in versus energy out, or spontaneous versus non-spontaneous, those are centered around 0 because we have negative values and positive values. Okay? There are no negative Ks, right? Because it's all concentrations. It's just more products versus more reactants. Okay? So this right here is sort of the translation between equilibrium constants and delta Gs. Okay? Comes directly from that. So let's calculate an equilibrium constant from a delta G. We can go either way with this. Okay? So this is the one that we had on the last page. This is a standard delta G. Okay? That means this is non-spontaneous. Non-spontaneous going forward. In other words, delta G means we start with 1 molar of everything. Going forward, what happens from there? Okay? Going forward, we're going to have condensation forming the liquid, like we said. Okay? So non-spontaneous going forward. Just from that, how would we predict the equilibrium constant for that would be? Less than 1, right? Because products over reactants should be reactant heavy. Although we don't have reactants in that, that just means we'll have a small amount of product. Okay? So, but let's do the calculation here. It's not a difficult calculation. Delta G minus RT natural log K. 8.59 kilojoules per mole. All right. So I think I gave you a R on the last page. 8.314 joules per mole Kelvin. Yep, we're going to have a minus there. But what can you already see about units here? Yep. So we probably better do divided by 1,000. 1,000 joules per kilojoule. Okay. In fact, just so we don't get anything confused, 8.314 joules per mole Kelvin. 1 kilojoule. Same thing. We're dividing by 1,000 either way. Okay. T, 25C is 298K. Then natural log of K. That's what we're solving for. Now be careful because we have capital K's here. This K is not the same as that K. This is Kelvin. It's kind of weird that it's the same unit here. This Kelvin cancels with that Kelvin. Joules cancel. And there's no unit over in here. Taking the logarithm of something removes its unit, and K doesn't have a unit. K and Q don't have units in the first place. Okay?
Why is taking the log or something to remove its unit?
Because the log is saying to what power did we raise a certain base. And exponents don't have powers to them. Okay? So the whole value itself may have some unit, but the logarithm is it's asking purely about the number, not the whole measurement. So the common logarithm says to what power did we raise the number 10? The natural logarithm is to what power did we raise the base e? Right? So, but that's irrespective of whatever unit that whole measurement happens to be. Okay? So, math-wise, I would just say 8.59 kilojoules per mole. This is going to be some negative number, right? 8.314 divided by 1,000 times 298. Negative 2.47757. Here's my color coding. Times natural log of K. Then what? So divide 8.59 divided by that answer negative 3.467. By the way, this over here was kilojoules per mole. So what happens to the unit when we do this divided by that? The unit cancels. Okay, so there's no unit over here. And then how do you solve for a variable inside of a natural logarithm? E to the k equals e negative 3.467. So I'm just going to do e to the answer. What did you guys get?
0.0312.
0.0312? Might be rounding.
I was using full number.
Yep, well, that's what I got. 8.99 divided by 2.47757. Yep, 2.467. E to the that 0.0312. Okay. What was our prediction about the size of K? Yep, less than 1. So overall, what a process we would consider to be non-spontaneous would have positive delta G, meaning from our starting point, we're going to be going backwards. Okay? The K would be less than 1, meaning that we'll be favoring reactants, right? Because it's products over reactants. That tells us, okay, let's look at this equilibrium right here. That tells us that when we're pure and 1 molar, we're going to be going backwards. And once we reach equilibrium, we're going to be reactant favored. Okay? So it's sort of like 2 points in time. Delta G standard is starting with everything at 1 and figuring out where we're going to go from there. K is sort of what is the composition of everything once we've reached equilibrium. Okay? But it's both sort of saying the same thing, just kind of versus at the start of the process or the end of the process. But they're going to be consistent with each other in that way. Does that make some sense? Okay, so what we can do, we could calculate K at, we could calculate K at 30 C. If you think back to vapor pressure, increasing the temperature does what to the vapor pressure?
Increase.
Yeah, it should increase the vapor pressure. All we would be doing here would be doing through, instead of 298, right, 30 plus 273.
303.
Yeah, you'd be doing 303 in there. Use 303 Kelvin. So it's pretty close, but 8.59. Combining all those things together using 303, I got minus 2.519. Oops, here. 2.519.142 times natural log of K divided by answer, oops, 8. e to the answer 330. So that's something that we have not done before. We pretty easily did a calculation that showed how an equilibrium constant changed with temperature. Okay? That's not something that we were really able to do before because temperature is more closely related to energy, and the equilibrium amount is just sort of an overall consequence of that. But once we have the calculations in terms of free energy available, temperature is just a term in that equation. We could use any temperature we like for it. Okay? So that's an advantage to that. Now, I want to, here. I'm going to keep going here, and we'll be able to apply this to a different equilibrium that we talked about. Ka is an equilibrium where a weak acid dissociates in water, right? Ka is the equilibrium constant. It's usually small because it is reactant favored at equilibrium. Okay? Now, what is delta G standard for the following equilibrium? Remember, think of our difference in perspective. Ka means that after all the dust has settled and this has reached equilibrium, we will be reactant favored, correct? Because products over reactants will be this very small value. Okay? But delta G standard looks at that from a different perspective. What do we start at when we're thinking about a delta G standard type thing? What are those standard conditions? For equal amounts of everything. And for aqueous solutions, what concentrations were we talking about? 1 molar for everything. Okay? So standard conditions conditions 1 molar for all solutions. So we could actually set up an ice table. We don't usually do ice tables like that because we're usually starting with no product and then making more product. And that's usually how we did ice tables. If we did an ice table like this, we would have to kind of go backwards, it turns out. So the reason we do most of our ice tables with no products is because we don't have to guess about what direction it's going to go. Okay? If we start with no products, we're always going to make some products, right? And you never have to guess about which way you're going to go. So when you're doing delta G, we start with 1 molar of everything, and then it's all about, does it go to the left or does it go to the right? Okay? So it's a sort of different kind of question that we're asking. But we can very easily do that if we have a Ka value. We can already pretty much predict what will happen if we know the behavior of weak acids. If we started with 1 molar of all of these aqueous things, what direction is it going to go if this is indeed a weak acid? Predict that we're going to go to the left, right? Predict delta G. That would be a delta G what? Mm-hmm. That would be non-spontaneous. Non-spontaneous from standard.
Why do we know that's going to the left?
So a couple of reasons. Ka is very small. Okay? The equilibrium constant for this is very small, which means after it's totally finished, products over reactants will be heavily favored to the reactants. Okay? Remember that. Ka, products over reactants. So if that's very small, that means reactants are favored at equilibrium. Okay? So if we start with 1 molar of everything, it's going to go this way to make more reactants. Okay? I think that's a better way of thinking of it. Okay? So we can calculate delta G, though, if we know K. delta G standard minus RT natural log of K. So 8.314 1 kilojoules, 1,000 joules. If you're not told, use 298. Okay. And then ln Ka, which we were not given, 2.3, 10 to the minus 9. So that's not any algebra, that's just typing. 8.314 divided by 1,000 times 298 times natural log 2.3 e minus 9. Okay. What'd you get? 49 point something? So times 8.314. 49.28.
Yes.
Kilojoules per mole. Okay.
Is delta G always in kilojoules?
It's in either kilojoules per mole or kilojoules. If you do the tabulation thing where you do coefficient times kilojoules per mole, then the per mole goes away.
Okay.
And you're doing it per a certain reaction. Okay? But if you're doing it just from R and T and something with no units, then it becomes kilojoules per mole. So, okay. So is that consistent with our prediction? Positive delta G, yeah, plus 49.28. Okay, consistent. Non-spontaneous. I guess that's what we're asking right here. Is it spontaneous under standard conditions? No. Non-spontaneous because more reactant will be produced when everything starts at 1 molar. And that's consistent with what we know about how weak acids are behave. They're mostly intact and not ionized. So if we start with 1 molar of everything, including intact and ionized, we're going to go backwards to make more intact molecules. Okay? So let's do one under non-standard conditions. We had an equation before. I've given you concentrations for all these things. These are obviously non-standard conditions. Okay, so what we need to do is figure out what Q is. Products, reactants. Let's say given. How about that? So if we look at our equilibrium, these two are our products, right? That's what it said up above, that we had HBRO and water making those two products. So 6.0, 10 to the minus 6. And we'll have that for hydronium and for BRO minus. So what do I have to do on the top of this fraction here? I have to square it, because we'll do that times itself. And at the bottom, we'll have 0.10. Okay. So I got 3.6 10 to the minus 10. That is Q. Okay. What we did before was compare Q with K to figure out if we're going to be going forward or if we're going to be going backwards from this, right? Because K is the endpoint. Q is where we happen to be starting with. When we did standard up there, we did it with Q equals 1 as our starting point. Here we're doing it with Q equals that as our starting point. So we go from Q to K, 3.6 e minus 10, to whatever K was, 2.3 e minus 9. Let's just hold that off to the side. The equation that I gave you before for a non-standard delta G that we didn't get to practice yet, non-standard is the standard delta G plus RT natural log Q. And again, what we said is we take a standard delta G, and then that will either go up or down based on where our Q is, where the reaction happens to be at the moment. Okay? So what was delta G standard? We calculated that, didn't we? 49.28. Plus RT. I'm not going to use units here. 8.314, as long as you remember to divide by 1,000. 298. ln of Q, 3.6 e minus 10. $49.28. Just to get your signs right, I really like just writing this number down, doing everything in here, and writing that number down, just so you don't get screwed up with signs. Checking my numbers here. Yep. Okay. So what's going to happen to the sign of delta G under these non-standard conditions? It's going to be negative, right? It's going to be minus 4.59 or something like that. What does that mean? It is now spontaneous. Meaning starting under these conditions with 0.10 molar of the reactant and very small amounts of the product, reaction will move to the right. Starting under standard conditions where everything was 1, the reaction moved to the left. But because standard conditions can be calculated in other ways, like from tables and stuff like that, we can use standard conditions to compare with what our actual conditions are at any particular point. Okay? It turns out that, let's see here, if this is smaller than K, right, which it is, which is right here, Q is smaller than K, that means we need to make more products. We talked about that before. If Q is too small, we need more products to make the top part of the fraction bigger to get to K. Okay? That's what happened here. We have a spontaneous reaction because this Q was smaller than K. Okay? Need more products. Simple way of saying that, I think. All right. If it were the other way around, if Q were larger than K, it would have been like our standard conditions, right? Standard conditions would be 1 going to that, okay? In which case we needed more reactants. Okay? So thinking of it in that way, I think that's a good. Let's just make a little table here. Standard conditions. Q will always go to K, okay? But Q of 1 will go to K, whatever K is, okay? Let's just use our values, 2.3 E minus 9. Okay? On our non-standard conditions, so let's say here we need more reactants. Need more products. Excuse me. One more. And there are consequences for delta G in both of those cases. When we're going in a direction where we need to make more reactants, what kind of delta G is that? Spontaneous or non-spontaneous? It's be non-spontaneous, so it's plus. So it's just write that right here. Delta G is plus. Need more products. Delta G negative. Excellent little summary for that. Okay? But of course, that depends on what the value of K is. This is just for this case. Okay? If we had a large K, if K was 10 to the 7 or something like that, we would go from standard conditions to make more products. Right? And if our non-standard conditions were even bigger than that, we would have to go backwards to make more reactants. Okay? So, thinking about Q approaching K, K being sort of like the end point, Q being whatever we start with, standard conditions means Q is 1. Okay? I think that's a nice way to think of it. And as a result, that's why we get this equation right here, okay, under standard conditions. Okay? We call Q, call that delta G 0. We end up with K happening right there. Okay, so this is just a little chart. Oh, good. That helps us visualize those changes that we were just talking about. Okay, so we've simplified it to an A reactant to B product equilibrium. Okay, A makes B, and if we start with K less than 1, that means at equilibrium, what would be favored if K is less than 1, A or B? A is favored. Okay, K is less than 1, so let's write that. A favored at equilibrium. Okay. So, standard conditions would be right here. Because at standard conditions, if these were gases, we would have 1 atmosphere of both of them. Okay? We would start with 1 and 1. Okay? So, going to equilibrium, I don't know, just do an example of 2 and 0.5. No, it has to be 1.5. We have to keep our stoichiometry, right? That would be consistent, right? So the way this graph works, if we start at standard conditions, that would be here, okay? Because on this x-axis, it is pure A versus pure B. So if we had 1 for both, we would be right there, okay? If we start with that, the reaction is going to produce more reactants, okay? Because we said K is less than 1. So we're going to go left on this kind of graph here until we run out of free energy. Free energy is what ultimately determines what happens spontaneously. So we would call that non-spontaneous, because if we mark B as the product, we are going away from B, right? So the free energy decreases, okay? This right here is delta G, going from standard conditions to equilibrium right here. So the thing is, it's yeah. That's I don't like that downwards delta G there. It's because here. Let's just write that non-spontaneous. Let's go backwards like that. It's non-spontaneous as written. Because in order to go in the spontaneous direction, you would have to say B makes A, right? Sort of the reverse of that, okay? So as written, A to B is non-spontaneous, okay? There is you could sort of think, yeah, it says right here, the reverse reaction is spontaneous. That's the way of thinking of it, okay? That B making A. I mean, it is spontaneous. That part is going downhill in the reaction, right? That itself is a decrease in free energy, but it would only be a decrease in free energy if we had it written B making A. Okay? Over here, it's a little more clear. If we start at standard conditions again, right? It's right there. And if K was greater than 1, okay, we would be going over this direction, making more B. Okay? That would be spontaneous as written. So non-spontaneous as written. So as written is important. I mean, that the way you write it doesn't change the reaction, but it changes the signs that we assign to that reaction. In other words, let's look at this example right here. If K equals 1, right? What would that mean if K equals 1? If this is a reaction where the equilibrium constant happens to be 1. Yeah, that means, remember, it's reactants over products. Okay? If K happens to equal 1 and all we have is A and B, that means that we would have both A and B in equal amounts at equilibrium. Okay? If K equals 1, the standard delta G would be what? Because standard conditions start with the same thing. So delta G, if K equals 1, delta G is 0. Okay? Delta G is 0 because we're already at equilibrium. And delta G standard okay? So you can see how this little standard thing is important. Okay? Under standard conditions, delta G is 0. But under non-standard conditions, this delta G could be whatever we like, right? Because non-standard conditions, we could be starting way over here, right? That would be spontaneous as written. Right? If we started over here, that would be spontaneous in the reverse direction. Because we would be making more A. Okay? So that's what I wanted to get through here, that in both, I mean, it's spontaneous, right? Something's going to happen unless it's already at equilibrium. Something is going to happen spontaneously. Just the question is whether it's spontaneous in the direction that we have written, or if it's non-spontaneous in the direction that we have written. Okay? That's sort of what the opposite is. That's really what a non-standard delta G means. Will the reaction be going in the direction we have written, or will it be going the other way? Okay? So that's why flipping an equation over changes the sign of delta G. We haven't changed anything about the reaction. We've changed the way we've written it, and we're just saying, is this spontaneous in the direction we have written or not? Okay? So since we have 5 minutes and I don't want to start chapter 18, I had a little problem that I wanted you to solve back on this one, and we'll just end with that. So go back to this page here. This is our non-standard, okay, based off of our standard. So we can actually calculate what will happen with this Q right here. Yeah, let's just do this. So the standard delta G up above, we said, was plus 8.59. Okay. RT 8.314 divided by 1,000. Let's say room temperature. Let's use this Q. Let's use this normal water vapor 5 times 10 to the minus 3. So we got 8.59. 8.314 divided by 1,000. 298. Log of 5. I got minus 13.1269. Five, 4. Okay. And here, you just forget about that question there. That didn't help things at all. What we wanted to say here on this one was that, remember those standard conditions, 1 molar for everything, water liquid, and 1 molar of water, 1 molar of water gas. Okay? That is non-spontaneous because you guys told me that water gas will condense under those conditions. Okay? Here, if we start out with normal air, water vapor in the air, we have standard delta G, but then take our non-standard conditions into account. This is spontaneous. So what does that mean if you have a glass of water sitting out in a room that happens to have 5 times 10 to the minus 3 atmospheres of water vapor?
It'll start to evaporate.
It will evaporate. Okay? And anything, so whether or not it evaporates depends on whether or not the air is saturated with water vapor or not. Right? So this obviously here is lower than the vapor pressure of water. If the water was 100% relative humidity, okay, then these two values would cancel each other out, and delta G would equal 0. Water will not evaporate when the air is saturated with water vapor. Okay? So, and if the air has more water vapor than at equilibrium, water will condense. Okay? So standard conditions are more water vapor than equilibrium. A normal room like this is usually less water vapor than equilibrium. If relative humidity is 30% or something like that, okay, water will evaporate. At the point where relative humidity is 100%, that's the point where delta G equals 0, and we're at equilibrium. We've reached K essentially for that process, right? So that's just a little more illustration about that. So you will be given that equation. Okay? This equation is what you use if you're ever given specific conditions for all your reactants and products. Okay? If you said, if you're told in the problem that the concentrations of these things are all this, or the concentration of this and that and that and that and that, if you're listed off all the concentrations, you get those into a queue, and you use those to modify the standard delta G. Okay? That's non-standard conditions. If all you're given is a K, okay, or if you're asked about K or something like that, you use this equation. Okay? Because the only way you can relate equilibrium constant with an energy is if you're doing that standard conditions, talking about whether you're going forward or whether you're going backward. That's directly related to the end point, whether you're going to have more reactants or more products. Okay? So it's really just knowing what circumstances to use those types of those equations in. Okay? So the one on the non-standard conditions, that's sort of a more specialty thing. This is a very, very important equation. I'm sure it's it deserves more credit than the 20 minutes or so that we spent on that. In graduate school, I took an entire course on thermodynamics that pretty much spent half of the time talking about equilibrium and free energy changes. But this, so obviously this just sort of scratches the surface. If you'll honestly be okay with it if you can plug values into these equations. Okay, like I said, the mistakes that students make are the unit, the kilojoules, and the negative signs. Okay. So if you're okay, so if you double check your units and double check your negative signs, you'll probably be okay in these equations. Okay? And then it's knowing context. Okay? That this is only standard conditions that gets you an equilibrium constant. If anything is other than 1 molar or 1 atmosphere or something like that, that's non-standard conditions. You have to use the other equation to adjust delta G. Okay? So do a little practicing with that. You're doing your mastering chemistry. This is mostly what your mastering chemistry is. Okay, it's going to be some with playing with the signs. What happens when delta H is plus and delta S is minus? It's going to be some of that, but it's going to be mostly using pretty much those 3 equations. Okay, and being able to understand and put into context what those things tell you. Okay. So questions? So yeah, practice through them in the mastering chemistry. Do enough of each of these types of calculations on your own so that you feel comfortable with them. Honestly, this exam will probably be pretty, I don't think there will be any surprises on this exam, right? You're going to have to do some calculations from here. You're going to have to say some things about how delta G and K are related, You're going to have to know what standard conditions are. Okay. In the buffers and titrations chapter, you're going to have to know how to set up those stand tables. Right? You're going to have to do something with the titration. So do a stand table and then the buffer calculation, or do the stand table and then if you've got just one thing, do an ice table. Right? If I were you, those would be the things I would concentrate on. That buffers and titrations worksheet gives you practice at every point along the titration curve. Okay? But all it is, you're always starting out with that stand thing that tells you where you are, and if you need to do the buffer calculation or the ice table after that.
So the worksheet you gave us,
Mm-hmm.
the K values that match with that, are those in the book? Because I tried it with the notes and I got slightly different answers for all of them.
Oh, that could be. Take a look in the take a look at the answer key and see where those.
They were slightly different.
They were slightly different. Maybe I need to update that. I might have got those from the old book or something like that. So.
Because I assumed that you did them.
Yeah.
Mm-hmm. Every time I do this,
Yeah. If you're a little bit, I wouldn't worry too much about it if you're a little bit off, because every table that you will access for K values will be a little bit different. So for mastering chemistry, use the book's K values.
I think it gives it to you.
Yeah. Use values it gives you. If it doesn't give you one, use it from the book. Don't use my K values, obviously. I would just go through and update all of my values to match the book, but I have other problems that make use of these ones that I would also have to update. So at some point, I'll just have to go through and update all of them.
Maybe it'd be easier to update to the book.
Yeah, but then at some point, we'll use a different book, and then I would have to go through and update those all again. So.